Hello everyone. Today we're going to talk about limit of a function and limit laws. Okay, so the idea is we're going to look at some function. So let's look at an example. So let's say our function f of x equals x squared minus 1 over x minus 1 act around x equals 1. And normally, if the function value existed at that point, we could plug it in and we'd know exactly what would happen at that point. But in this case, 1 is not in the domain, but we can see what's happening at 1 as well. All right, so let's look at this function. So we have x squared minus 1 over x minus 1. This is the same thing as saying x plus 1, x minus 1, divided by x minus 1. So really this is x plus 1, but there's a point in the domain that doesn't exist. We know x can't be 1. So we have to also say x is not 1. So we have x plus 1, but x is not allowed to be 1. So this is the graph of x plus 1 with a hole. Sorry, not the right spelling of hole. Hole at x equals 1. So we have the line x plus 1, but we're going to have a little hole in it where the point is not defined. So we know f of 1 is not defined. But we can take a pretty good guess that it's going to be a very close point to 2. So when we get really close to 1, it's going to be about 2. So we say the value would be about 2. We'll say close to 2. So this is very informal. The point doesn't exist, but as we're approaching that point 1, we're also approaching 2 for the y value. So I'm going to give you a definition, and I'm going to call this the informal definition. So this is our informal definition of a limit. So we write we're going to say the limit as x goes to c of f of x is equal to L. And we say this as the limit of f of x as x approaches c is L. If we want to write it, we would write it in words. We say the limit of f of x as x goes to c. We do a little arrow. So as x approaches c is L. So in the above example we just did, we would say the limit as x approaches 1. So we know we can't equal 1 of our function f of x is equal to 2. So the limit would exist in this case, but the value does not exist in this case. So actually all three of these functions that I'm about to give you have this same limit. So this is a true statement for all of these. So example, so all have the same limit. So the one we looked at originally, we had f of x is x squared minus 1 over x minus 1. We could also write f of x equals x squared minus 1 over x minus 1 if x is not 1. And then we could also say we'd have if x is equal to 1, so if we want this limit to be true, our y value would be 2. Right? Or we could just use the line. If I said f of x equals x plus 1, at 1 these all have the same limit. The limit as x approaches 1 of these three functions are all 2. So they're very different functions, but we all have the same limit. Right. So let's look at a few examples of just some simple limits. So let's find the limit of the identity function. So let's consider f of x is equal to x for any c. So we have f of x equals x for any c. So the limit as x goes to c of our function. So if we go to any value c, our function is just f of x equals x. We can just plug in c. So if it exists and I can just plug that number in, go ahead and plug that number in. So if I plug in c for x, clearly the limit as x goes to c of x would be c. So for the identity function, the limit of where x is approaching is also the value of the limit. Right? And another quite trivial example is the constant function. So if we consider f of x equals k for any c, we have the limit as x goes to c of f of x equals the limit of x goes to c of k, so some constant. It's just a constant function, so we know that it has to be that constant value. So if I have the function y equals 2, we know no matter where I pick, the limit's going to be 2, because that's the only value of the function. So I'm going to give you a second to think now. I'm going to give you 3 different functions, and I want you to think why do these might not have a limit. So you don't have to explain it formally or give a reason. Just think about what happens in these functions. Try and draw these functions. Try and graph them. Plug them into a graphing calculator. See what happens. And then let's try and figure out why there's no limit. So why do these functions not have a limit as x goes to 0? Right? So function 1, we'll say, I'll call them all f. Let's say f of x is 0 and 1. Say this is x is less than 0, x is greater than 0. So think about what that graph might look like. In the review unit, we looked at this function, 1 over x squared. I'll say if x is not 0, and then we'll make this a piecewise as well. We'll give you the value 0, 0, and then fg, and I'll call this one h, I guess. fgh, we'll say 0 if x is less than or equal to 0, and I'll do sine 1 over x is greater than 0. So go ahead, graph these functions. You can look them up in Desmos if you'd like. Any way you can see what they look like. And pause this video, try and think about it. Okay, so for f of x, this is what we call a function that has a jump. So we say this jumps at x equals 0. So the function, when x is less than 0, is just a line at 0. How we draw this one? So we have a line at 0. And then when we get to 1, we have an open circle here. When we get to 1, or we get to 0, we jump to 1, and then it would look like this. So we jump at 0. We jump from 0 to 1. We looked at 1 over x squared in our review unit, and we see that it has asymptotes. So since it has asymptotes, we don't actually have a value at 0. We say this is unbounded at 0. So even though we have that point, it doesn't make a difference. I have a point 0, 0. That's okay. But if we're looking where the function approaches from both sides, it's headed towards infinity. It's unbounded when we go towards 0. And then our last one, this one's a little tricky one. So we'll take a look at the graph. So I said it's 0 until we get to 0. And then sine 1 over x is a function that oscillates a bunch. So it looks something like this. It goes up and down really fast. I would recommend typing that one into Desmos just to get a good idea of what it actually looks like. That's the best I can draw it. But we say this oscillates too much. So those are 3 different reasons why a limit may not exist. And that's a question that I might ask you. All right. Let's talk about a few limit laws. All right. So for all of these, we'll say if f of x, sorry, the limit as x goes to c of f of x is equal to L, and we'll say the limit as x goes to c of, we'll say, g of x is equal to m. Then, if we take the limit as x goes to c of f of x plus g of x, this is the same thing as L plus m. So if we add 2 functions together, the value is just the value of adding the limit values together. So we can add L and m if we're taking the addition of 2 limits here. The same thing would apply if we had subtraction. If I have f of x minus g of x, this would be L minus m. I can multiply by a scalar. So if I call this, let's say, k times, either one would work. We'll do k times f of x. So k times f of x would be just k times L. I can multiply the functions as well. So if I do f of x times g of x, this is L times m. So if I can multiply, I can also divide them. So I do f of x divided by g of x. It's important to note here, though, that we can't divide by 0. So if g of x is equal to 0, then the limit would not exist. So I'll write it as m can't be 0. I could also take a power. So if I have a function f of x, and we raise it to, let's say, the n power, and we get L to the n. And since we're raising this to a power, remember, we can use a fractional power. That means it also would apply to any nth root as well. So power could be squared, but it could be a half. It could be the square root. So either one would be okay. So these are our limit laws. So we're going to use some examples now to take a look at these limit laws. All right. So if I take the limit of x going to c of, let's say, x to the third plus 4x squared minus 3. Let's say I have the limit as x goes to c of x to the fourth plus x squared minus 1 over x squared plus 5. And then we'll do one more. Let's do the limit as x goes to negative 2 of the square root of 4x squared plus 3. All right, so take a minute, pause the video, and give those a try, and then we'll take a look. Okay, so for our first one, we're able to just plug in our c. So we have c to the third plus 4 times c squared minus 3. So very straightforward. We're just plugging in c. This one as well, c to the fourth plus c squared minus 1, and then c squared plus 5. Okay. And then when we plugged in c for these first two, so we can imply that we plug in negative 2 now. So I'd have 4 times negative 2 squared plus 3. That would give me 4 times 4 is 16 plus 3, which would give me the square root of 19. So let's make sure we throw some equal signs in here as well. So let's look at a little more complicated of an example now. Let's say we have the limit as x goes to negative 1 of x to the third plus 4x squared minus 3 divided by x squared plus 5. All right. Here, we're plugging in negative 1. So I have in my numerator, I have 0. In denominator, I would have 6. So this one, we would have 0 divided by 6, which is 0. So this is okay. And so if I have 0 in my numerator, it clears everything out. We get 0. That's okay. What I have to watch out for is if I get 0 in the denominator. So if I had, let's say, this one, the limit as x goes to 1 of x squared plus x minus 2 over x squared minus x. If I plug in that 1, I'm going to have 0 in my numerator, and I'm going to have 0 in my denominator as well. So what I can do is I can simplify it. So we can't do 0 divided by 0. That's undefined. So what I do is I can factor. X squared plus x minus 2, remember, is equivalent to x minus 1. X plus 2. And then that's denominator. I could factor out an x. We'd get x minus 1, which would allow my x minus 1s to cancel out. So I'd have x plus 2 over x. So let's rewrite this. This is the limit as x approaches 1 of x plus 2 over x. All right. And then we get 3. We plug in a 1. 1 plus 2 is 3. Divided by 1 would give me 3. But we have to just make sure we say that x cannot be 1. So we can approach 1, but we can't equal 1. Okay. So let's look at another one. Let's say we have a square root. Let's say I have the limit of x goes to 0 of x squared plus 100 minus 10 over x squared. All right. So right away, I take a look at this. I can't plug in 0. I'll get 0 divided by 0, or even in the denominator right away, I know I get 0. So we have to try something new. So if we have a square root, we can use the rule of a difference of two squares. So we multiply by what's called the conjugate. So if when multiplying by the conjugate, I'm going to have a minus b, a plus b, which we know is a squared minus b squared. So the conjugate, meaning I'm going to flip the sign here. So x squared plus 100, instead of minus 10, we're going to have plus 10. And we're going to multiply that to the numerator, which means I also have to multiply it to the denominator. Which just might seem a little weird because we normally don't like to have square roots in the denominator, but it's okay because I'm going to end up plugging in a 0 and my square roots will go away. Okay, so we now have in my numerator x squared plus 100 in the square root times the square root of x squared plus 100 is just x squared plus 100. We have x squared plus 100. 10 times 10 is 100, so a squared minus b squared give us minus 100. And then we have over x squared times x squared plus 100 plus 10. Okay, so now that we have this, in my numerator, my x squareds, or my hundreds will cancel out. So I have x squared over x squared. So 100 minus 100 is 0. My x squareds can cancel out. So I'd have 1 over the square root of x squared plus 100 plus 10. So now let's take the limit as x goes to 0 of 1 over square root x squared plus 100 plus 10. So when I plug in 0, I get square root of 100 plus 10, which is 1 over 20. Or we could call that 0.05. Either or would be perfectly fine with me. All right. So the two common strategies we're going to use when we deal with limits. So we can either try and factor and cancel out a term, but if we can't factor and we have something like that, we might just have something that's undefined. That is possible. But we should always try and factor. Most of the time something will cancel out, and then it'll be a solvable problem. If I have a square root, a good guess is always to go to the conjugate. Right. So the last exercise we're going to look at today, we're going to use this theorem. The theorem is called the sandwich theorem. Right. So we're going to suppose we have g of x is less than or equal to f of x, which is less than or equal to h of x for all x. Okay. In some interval, we'll say containing c. Right. Except for maybe x equals c itself. So this piece, it could equal x equals c, that's okay, but we just exclude it to be safe. So if we have these conditions, it's a true statement if the limit as x goes to c of g of x is equal to L, and the limit as x goes to c of h of x is equal to L. This is going to imply the limit as x goes to c of f of x would have to equal L. So if the interval is from g of x to h of x, or we look at our interval and g of x and h of x, we take the limit, we get L. That means the limit of that inside function in our inequality also would have to be L. So we're sandwiching in that function. So if we want to look at an example of this, let's look at, we'll say f of x equals x squared sine 1 over x squared. Okay? And we're going to look at x equals 0. So we can't plug in 0 here. I can't do sine 1 divided by 0. That point does not exist. But what we could do is consider two outside functions here. So we know that this fact is true. If we have -1 is less than or equal to sine 1 over x squared, which is less than or equal to 1. So my two outside functions right now, at the time being, are just -1 and 1. And I know this is a true statement because sine 1 over x squared, the sine function, the minimum value is -1, the maximum value is 1. But this is not the function we have. We have x squared times sine 1 over x squared. So let's go ahead and multiply this whole thing by x squared. That doesn't change anything. So I'd have minus x squared is less than or equal to 1. Oops. Let's not forget the sign part. So minus x squared, multiply x squared to the middle, and then multiply x squared to the outside. All right. So now we have our three functions. G of x is minus x squared, h of x is x squared, and f of x is our inside function now. Okay. And this math is okay. By multiplying an inequality all by the same value, does not change the inequality. So if I take the limit as x goes to 0 of minus x squared, I get 0. If I take the limit as x goes to 0 of x squared, I plug in 0 squared, it's also 0. So this implies then the limit as x goes to 0 of x squared sine 1 over x squared, that would also be 0. So we call that the sandwich theorem. That's it for today for our informal definition of a limit. Next time we're going to talk about the precise definition of a limit. I hope everyone has a great day, and I'll see you all next class.